A report suggests that the findings of the James Webb Space Telescope have undermined the case for the Big Bang. The universe as we know it began with a Big Bang, a singular cataclysmic event that occurred approximately 13.8 billion years ago. This explosion not only gave birth to space and time, but also laid the groundwork for everything that exists: the galaxies, stars, planets, and even life itself. For decades, this model has served as the cornerstone of modern cosmology. It provides a coherent explanation for the observable universe, backed by robust evidence like the cosmic microwave background radiation and the redshift of distant galaxies. But what happens when observations contradict the fundamental assumptions of this theory? What do we make of discoveries that seem impossible, defying everything we thought we understood? Recent findings from the James Webb Space Telescope have thrust these questions into the spotlight, suggesting that the universe might not be as straightforward as we believed. The telescope has captured images of galaxies that appear to be older than the Big Bang itself. Yes, you heard that right. Galaxies that, by all accounts, shouldn't exist. The implications of this discovery are staggering. If these observations are correct, they force us to rethink not just the Big Bang, but our entire understanding of the cosmos. It's as if the universe is telling us that we've overlooked something fundamental, that there's a deeper truth waiting to be uncovered. And the more we examine these enigmatic galaxies, the more questions arise. How is it possible for structures to exist before the universe was even born? What does this mean for the laws of physics? And could it be that the universe is part of a cycle far grander and more complex than we ever imagined? To fully appreciate the significance of these discoveries, we need to understand what the James Webb Space Telescope was designed to do. As the most powerful space observatory ever built, Webb was launched with the ambitious goal of peering deeper into the universe than ever before. Its advanced infrared capabilities allow it to see through clouds of gas and dust, revealing the hidden structures of the cosmos. It's like a time machine, capturing light from the earliest epochs of the universe. Webb's mission is rooted in the idea that by studying the distant past, we can better understand the present. When we observe a galaxy billions of light years away, we're seeing it as it was billions of years ago, because that's how long its light has taken to reach us. This makes Webb an invaluable tool for exploring the early universe, providing a window into the formation of the first stars and galaxies. But what Webb has found is far more perplexing than anyone anticipated. Among its early observations were galaxies that appeared to exist just a few 100 million years after the Big Bang. These galaxies are remarkably massive and well-structured, challenging existing models of cosmic evolution. According to the standard timeline, there simply shouldn't have been enough time for such large and organized structures to form. At first, scientists thought these findings could be explained by recalibrating their models or adjusting for observational biases, but as Webb continued its work, it uncovered something even more astonishing: galaxies with redshifts so high that they appear to predate the Big Bang itself. These redshifts suggest that the light from these galaxies has been traveling for more than 13.8 billion years, implying that they existed before the universe's supposed origin point. This discovery raises profound questions about the nature of time and space. Could it be that our understanding of the Big Bang is incomplete? Is it possible that the universe existed in some form before this event? And if so, what does that mean for our theories about the origins of reality? One potential explanation is that the Big Bang wasn't the true beginning of the universe, but rather a transition from a previous state. This idea is not new. It's been explored in various forms by cosmologists and physicists. For example, some theories propose that the universe undergoes cycles of expansion and contraction, with each Big Bang representing the birth of a new phase. In this view, the galaxies observed by Webb could be remnants of a previous universe, surviving the transition into our own. Other theories suggest that the Big Bang was not a singular event but part of a larger multiverse. In this framework, Our universe is just one of countless others, each with its own laws of physics and timelines. The galaxies spotted by Webb could belong to a neighboring universe, their light somehow leaking into ours through a phenomenon known as quantum tunneling or a wormhole-like structure. These ideas, while speculative, are grounded in serious scientific inquiry. They challenge us to think beyond the constraints of our current models and consider the possibility that the universe is far more complex than we ever imagined. But they also raise difficult questions about how we can test and validate such theories. If the galaxies observed by Webb truly predate the Big Bang, how can we prove it? What kind of evidence would be required to overturn a theory as well established as the Big Bang? To answer these questions, we must delve into the data itself. Webb's observations are based on the redshift of light, which measures how much the wavelength of light has been stretched as the universe expands. The higher the redshift, the farther away and therefore older a galaxy is. But interpreting redshift data is not straightforward. It requires precise measurements and careful calibration, as well as a deep understanding of the astrophysical processes that affect light as it travels through space. Some scientists have suggested that the anomalous redshifts could be the result of errors or misinterpretations. For example, dust within the galaxies themselves could affect the light spectrum, making it appear older than it actually is. Alternatively, the galaxies could be much closer than they seem, with their apparent redshifts caused by unknown factors. However, these explanations have not been able to fully account for the data, leaving the mystery unresolved. Another possibility is that our understanding of cosmic expansion is incomplete. The standard model assumes that the universe has been expanding uniformly since the Big Bang, but what if this isn't the case? What if there are regions of the universe where the rules are different, where time and space behave in ways we don't yet understand? Such anomalies could explain the existence of galaxies with extreme redshifts, but they would also force us to rewrite the laws of cosmology. Michio Kaku, a prominent theoretical physicist, has spoken about the need to remain open-minded in the face of such discoveries. He argues that the universe often defies our expectations, revealing truths that are stranger than fiction. In his view, the Webb telescope's findings could represent a turning point in our understanding of the cosmos, one that challenges the very foundations of physics. Kaku has also emphasized the importance of exploring alternative theories, such as string theory and quantum gravity, to explain these anomalies. These frameworks propose that the universe operates on multiple levels, with dimensions and forces. Theories that are hidden from our perception. If these theories are correct, they could provide a basis for understanding how galaxies older than the Big Bang could exist. One intriguing possibility is that time itself is not linear but cyclical. In this model, the universe doesn't have a singular beginning or end, but exists in an eternal loop. The Big Bang would represent a moment of rebirth, a transition from one cosmic cycle to the next. This idea is supported by certain interpretations of quantum mechanics and the concept of time as an emergent property rather than a fundamental aspect of reality. Another possibility is that the universe is holographic in nature, with the three-dimensional world we experience being a projection of information encoded on a two-dimensional surface. This idea, known as the holographic principle, has gained traction in recent years as a potential explanation for various cosmic phenomena. If the universe is indeed a hologram, it could provide a framework for understanding how galaxies older than the Big Bang could exist, as they might represent information from a previous iteration of the cosmos. The discovery of these galaxies also raises philosophical questions about the nature of existence. If the universe is part of a cycle or a multiverse, what does that mean for our place within it? Are we simply observers in an endless cosmic dance, or do we have a greater role to play? And what does this tell us about the origin of life and consciousness? These questions are not just academic. They have profound implications for how we see ourselves and our relationship to the universe. They challenge us to think beyond the boundaries of our current knowledge and embrace the possibility that reality is far more intricate and mysterious than we can comprehend. As the James Webb Space Telescope continues its mission, it will undoubtedly uncover more surprises. Each new discovery will add to our understanding of the cosmos, while also raising new questions. The search for answers will require a combination of cutting-edge technology, creative thinking, and an openness to reimagining the laws of physics. The galaxies older than the Big Bang represent more than just a scientific puzzle. They are a reminder that the universe is full of wonders and mysteries waiting to be uncovered. They challenge us to look beyond our assumptions and confront the unknown, pushing the boundaries of what we thought was possible. In the end, the universe may not conform to our expectations. It may be stranger, more complex, and more beautiful than we can imagine, but that is what makes the search for understanding so exciting. It's a journey that will continue to inspire and challenge us, leading us to new horizons and deeper insights into the nature of reality. The discovery of galaxies that seemingly predate the Big Bang has captivated scientists and challenged the core principles of modern cosmology. The implications of these findings are staggering. They don't merely add a wrinkle to our understanding of the universe. They call into question the very fabric of the cosmic narrative we've constructed over centuries. But what if this isn't the first time such anomalies have surfaced? As we dive deeper into this mystery, we must explore how previous discoveries, both recent and historical, hint at the possibility that our understanding of the universe may have always been incomplete. One of the most remarkable aspects of the James Webb Space Telescope's observations is how quickly they overturn some of the most cherished assumptions of cosmology. This isn't the first time a new tool has revolutionized our understanding of the universe. In the early 20th century, Edwin Hubble's observations fundamentally changed the way we view the cosmos. Before Hubble, scientists believed the Milky Way was the entirety of the universe. Hubble's discovery of other galaxies and their redshifts indicating expansion completely transformed our perception of reality. Similarly, the discovery of the cosmic microwave background radiation in 1964 by Arnold Penzias and Robert Wilson was a watershed moment, providing what seemed to be definitive evidence for the Big Bang. This faint glow of radiation, left over from the early universe, became a cornerstone of modern cosmology. And yet, here we are once again questioning the framework that has guided us for decades. It's worth considering that every time humanity has developed new observational tools, we've encountered surprises. The James Webb Space Telescope, with its unprecedented sensitivity and ability to peer into the distant past, is no exception. But this time, the surprises are of an entirely different magnitude. Let's take a closer look at the galaxies in question. These are not faint, barely visible structures. They are large, luminous, and surprisingly well-formed. This is particularly strange because, according to the standard model of cosmology, the early universe was a chaotic place. The first few 100 million years after the Big Bang were dominated by a dense, hot soup of particles with no stars or galaxies to speak of. As the universe expanded and cooled, gravity began to pull matter together, forming the first stars and galaxies. But this process takes time. The first stars, known as population 3 stars, are thought to have been massive, short-lived, and composed almost entirely of hydrogen and helium. These stars would eventually explode in supernovae, seeding the cosmos with heavier elements necessary for the formation of later generations of stars and galaxies. This gradual process should mean that the earliest galaxies are small, irregular, and chemically simple. Yet, the galaxies observed by Webb defy these expectations. They are massive, containing tens or even hundreds of billions of stars. They show evidence of complex chemical compositions, suggesting that multiple generations of stars have already lived and died, and they exhibit structures, spiral arms, bulges, and disks. that seem far too mature for their age. If these galaxies truly existed before the Big Bang, then what we are observing is not just an anomaly, it's an outright paradox. Theories abound, but each one raises as many questions as it answers. Some scientists have suggested that these galaxies might not actually predate the Big Bang, but instead exist within a different kind of timeline. In this view, time itself may be more complex than we currently understand. The concept of linear time, with a clear beginning and end, could be an oversimplification. If time is cyclical or multidimensional, it might allow for the existence of structures that appear to predate the universe as we know it. This idea finds some support in theoretical physics, particularly in models involving string theory and quantum gravity. These frameworks suggest that our universe might be part of a larger multiverse, with each bubble universe having its own timeline. In such a scenario, the galaxies observed by Webb could belong to a neighboring universe, their light crossing into ours through some yet unknown mechanism. Another possibility is that these galaxies are remnants of a previous cosmic cycle. This idea is central to certain cyclic cosmological models, which propose that the universe undergoes endless cycles of birth, expansion, contraction, and rebirth. In this framework, the Big Bang is not the beginning of everything but merely a transition point in an eternal process. If this is the case, the galaxies observed by Webb might have formed during a previous cycle, somehow surviving the transition into our current universe. But how could such remnants survive the unimaginable energies and transformations associated with a cosmic rebirth? To answer this, we might need to rethink our understanding of matter and energy at fundamental scales. Some theories suggest that under extreme conditions, such as those at the end of a cosmic cycle, matter could be compressed into forms that are stable enough to persist across transitions. These primordial seeds could then act as the building blocks for new structures in the next cycle. Other researchers have proposed even more radical ideas. One such theory posits that the Big Bang itself might not have been a singular event, but rather part of a more complex process. For example, some models suggest that the universe could have been born from the collision of higher-dimensional branes within a larger multiverse. In this view, the Big Bang represents the moment when our particular brane gained enough energy to expand and form a universe, but it doesn't necessarily mark the beginning of time itself. If this theory is correct, then the galaxies observed by Webb could be echoes or projections of structures that existed in the higher dimensional space before our universe came into being. This would mean that the universe we observe is just a slice of a much larger reality, one that includes dimensions and phenomena beyond our comprehension. These ideas may sound like science fiction, but they are grounded in serious scientific inquiry. Theoretical physics often operates at the boundaries of what we can observe and measure, exploring possibilities that challenge our intuition. And while these theories may be speculative, they are not without precedent. In the past, many ideas that seemed far-fetched, such as the existence of black holes or the accelerating expansion of the universe, were eventually confirmed through observation. The discovery of galaxies that appear to predate the Big Bang also forces us to confront the limitations of our current models. The standard model of cosmology, known as lambda cold dark matter, has been remarkably successful in explaining many aspects of the universe. It accounts for the distribution of galaxies, the behavior of dark matter, and the evolution of cosmic structures, but it is not without its shortcomings. For example, the standard model struggles to explain certain aspects of galaxy formation and evolution. Observations of galaxy clusters, such as the Bullet cluster, reveal behaviors that are difficult to reconcile with the model's assumptions. Similarly, the nature of dark matter and dark energy, two of the most important components of the model, remains elusive. Despite decades of research, we still don't know what these entities are or how they fit into the broader picture of the cosmos. The James Webb Space Telescope's findings add another layer of complexity to this puzzle. If these galaxies are real and their redshifts are accurate, then the standard model cannot account for them. This doesn't necessarily mean the model is wrong, but it does suggest that it is incomplete. There may be factors or phenomena that we have yet to discover, elements of the cosmic story that remain hidden. This is where the scientific method shines. Rather than rejecting anomalies outright, scientists use them as opportunities to refine their theory. The history of science is filled with examples of observations that initially seemed inexplicable, but ultimately led to breakthroughs. The discovery of galaxies older than the Big Bang may be one such moment, a turning point that forces us to think differently about the universe. As we grapple with these mysteries, it's important to remember that science thrives on questions. The more we learn, the more we realize how much we don't know. This humility is at the heart of scientific progress. It's what drives us to build instruments like the James Webb Space Telescope, to push the boundaries of our understanding, and to explore the unknown. The universe is a vast, complex, and deeply mysterious place. It challenges us at every turn, forcing us to confront our assumptions and expand our horizons. The discovery of galaxies older than the Big Bang is a reminder that the cosmos is full of surprises, that the answers we seek are often stranger than we can imagine. In the coming years, the James Webb Space Telescope will continue to explore the universe, uncovering new mysteries and deepening our understanding of the cosmos. Each observation will bring us closer to the truth, even as it reveals new questions. And as we journey further into the unknown, we will undoubtedly encounter more anomalies, more puzzles, and more opportunities to rethink the nature of reality itself. The discovery of these galaxies is not just a scientific milestone. It's a testament to humanity's insatiable curiosity and our unyielding desire to understand the universe. It reminds us that the cosmos is not just a collection of stars and galaxies. It is a story, one that we are still learning to read. The universe may be stranger than we think, but it is also more beautiful, more intricate, and more awe-inspiring than we could ever have imagined. And as we continue to explore its depths, we can take comfort in the fact that every question brings us one step closer to understanding our place in this vast, mysterious cosmos. The discovery of galaxies that seem to predate the Big Bang strikes at the very core of our understanding of reality. It's not just a challenge to a scientific theory. It's a riddle that forces us to confront the limits of human knowledge. What's particularly fascinating is that this isn't the first time our models of the cosmos have been upended. History is rich with moments when the universe revealed itself to be more complex and surprising than we dared to imagine. Consider the Copernican revolution. Before the 16th century, the prevailing model of the universe placed Earth at the center of everything. The sun, planets, and stars were thought to revolve around us in perfect celestial harmony. This geocentric model, rooted in Aristotelian philosophy and ancient astronomy, was deeply ingrained in both scientific and cultural thought. But Nicholas Copernicus dared to suggest otherwise. His heliocentric model, which placed the sun at the center of the solar system, was revolutionary. It challenged not only scientific assumptions, but also deeply held beliefs about humanity's place in the cosmos. The implications were profound. Earth was not the center of creation, but one of many planets orbiting a distant star. At first, Copernicus' ideas were met with skepticism and resistance. They seemed to contradict common sense and centuries of established thought. But over time, evidence mounted in favor of the heliocentric model. Observations by Galileo Galilei, Johannes Kepler's laws of planetary motion, and Isaac Newton's theory of gravity provided the framework to understand this new cosmic order. The lesson here is that paradigm shifts often begin with anomalies, observations that don't fit the established model. These anomalies challenge us to think differently, to question what we thought we knew. The discovery of galaxies that appear older than the Big Bang could be the anomaly that sparks the next great revolution in cosmology. To understand why this discovery is so groundbreaking, we need to revisit the Big Bang theory itself. This model, developed in the early 20th century, is based on the idea that the universe began as an infinitely dense, hot point known as a singularity. From this state, the universe expanded and cooled, eventually forming the structures we see today. The Big Bang theory is supported by multiple lines of evidence. The first is the observation that galaxies are moving away from us, as discovered by Edwin Hubble in the 1920s. This redshift of light suggests that the universe is expanding, implying it was smaller and denser in the past. The second line of evidence is the cosmic microwave background radiation, a faint glow that permeates the universe, discovered in 1964. This radiation is thought to be the afterglow of the Big Bang, providing a snapshot of the universe when it was just 380,000 years old. The third line of evidence comes from the abundance of light elements like hydrogen, helium, and lithium. The proportions of these elements match predictions made by models of nucleosynthesis in the early universe. Together, these observations form a compelling case for the Big Bang. But like any scientific theory, it is not immune to revision. The discovery of galaxies that appear to predate the Big Bang challenges the theory's assumption that the universe has a single, well-defined beginning. One possible explanation for these galaxies is that they exist in a kind of pre-Big Bang state. This idea finds support in certain interpretations of string theory and loop quantum gravity, which suggest that the universe has a cyclical nature. In this view, the Big Bang is not the ultimate beginning but rather a transition from a previous phase of the cosmos. String theory, for example, proposes that the fundamental building blocks of the universe are not particles, but tiny vibrating strings of energy. These strings exist in higher dimensional space, which could allow for phenomena that seem impossible in our three-dimensional world. If the universe is part of a higher dimensional multiverse, then the Big Bang might be just one of many such events. Loop quantum gravity offers a different perspective. This theory suggests that space and time are not continuous but instead composed of discrete, quantized units at extremely small scales, such as those present during the Big Bang. These units could create a balance, allowing the universe to transition from a contracting phase to an expanding one. Both of these theories challenge the traditional notion of a singular beginning. They suggest that the universe is part of a larger, more complex system, one that operates on scales and dimensions beyond our current understanding. But what if the galaxies observed by the James Webb Space Telescope are not remnants of a previous cycle, but instead part of a parallel universe? The concept of a multiverse has gained traction in recent years, particularly in the context of inflationary cosmology. Inflation theory, developed in the 1980s, proposes that the universe underwent a rapid expansion in the first fraction of a second after the Big Bang. This expansion smoothed out irregularities and set the stage for the formation of galaxies and other structures. However, inflation also predicts that our universe might be just one of many pocket universes, each with its own physical laws and properties. If this multiverse exists, then the galaxies observed by Webb could belong to a neighboring universe. Their light might have reached us through some kind of interdimensional interaction, such as quantum tunneling or a wormhole. While this idea is speculative, it aligns with certain interpretations of string theory and quantum mechanics. Another possibility is that our understanding of time is fundamentally flawed. The concept of time as a linear progression from past to future is deeply ingrained in our thinking, but it may not reflect the true nature of reality. Some physicists suggest that time is an emergent property arising from the interactions of fundamental particles. If time is not fundamental, then the distinction between before and after the Big Bang might not be as clear-cut as we assume. In this view, the galaxies observed by Webb could exist in a kind of timeless state, their existence not bound by our conventional understanding of chronology. These ideas are profoundly challenging, not just scientifically but philosophically. They force us to confront questions about the nature of existence, the origin of the universe, and our place within it. Are we part of a grand cosmic cycle, endlessly repeating? Is our universe just one of countless others, each with its own story? And what does it mean to exist in a universe that defies comprehension? The discovery of galaxies older than the Big Bang also has implications for the search for extraterrestrial life. If the universe is older or more complex than we thought, then the conditions for life might be far more diverse than we imagined. Life could exist in forms and environments beyond our wildest dreams, shaped by physical laws that differ from those in our universe. This raises profound questions about the nature of intelligence and consciousness. Are we unique, or are there other beings in the cosmos who ponder the same questions? And if so, how might they perceive the universe? Could they have already grappled with the mysteries that now confront us? The search for answers will require a combination of observation, experimentation, and theoretical innovation. The James Webb Space Telescope is just the beginning. Future missions, such as the Nancy Grace Roman Space Telescope and proposed next-generation observatories, will build on Webb's discovery, probing even deeper into the universe's history. At the same time, advances in theoretical physics will continue to push the boundaries of our understanding. Concepts like quantum gravity, extra dimensions, and holographic principles are still in their infancy, but they hold the potential to revolutionize our view of the cosmos. As we explore these frontiers, it's important to remember that science is a process, not a destination. Each discovery raises new questions. Each answer reveals new mysteries. The journey of understanding is never-ending, and that is what makes it so exciting. The discovery of galaxies older than the Big Bang is a reminder of the universe's infinite complexity and wonder. It challenges us to think beyond our assumptions, to embrace the unknown, and to push the boundaries of what we can comprehend. In the end, the universe is not just a collection of stars and galaxies. It is a story, one that we are only beginning to understand. And as we continue to explore its depths, we can take comfort in the fact that the greatest mysteries are still ahead of us.